Welcome to Spring LIB.
This is chapter 37, problem number 68. We have a system of binary stars, and we're given the frequency of a heated hydrogen gas measured on Earth. I'm going to call it F naught, 4.5681 times 10 to the power of 14 hertz. This will be 14. And the frequency of the hydrogen gas that is received from the stars, it varies in frequency. So the higher frequency, I'm going to call it F plus, it's 4.56891 times 10 to the power 14 hertz. And the lower one that is measured is 4.56771 times 10 to the power 14 hertz. Now let's remember the figure. We have two stars with the orbital velocities. So they're rotating around their central mass, and this portion, this shows the direction of the Earth. Now, let's write down what V is. This is the orbital velocity. Let's also define as U as the velocity of the central mass. Velocity of center of mass. And now we're going to make an assumption. We're going to assume that it is already approaching Earth. And if at the end we find it out to be negative, then it's going to be the other way around, moving away from Earth. But if it comes out to be positive, then it's coming towards Earth, and we were right from the beginning. And now assuming that, if you use the relativistic Doppler frequency equation, so the plus is going to be C plus U plus V. I'm writing this for the upper star here. That's why I'm adding the velocities together, because the velocity of the center of mass is in the same direction as the orbital velocity, and divided by C minus U plus V, F naught, right? And this would be the frequency that we're measuring is higher, because as you know from the conceptual portion of this topic, that if the object is approaching the observer, we're actually detecting a higher frequency emanating from it. Now, if we do the same for the second star, the only difference is going to be now the direction of these two velocities, U and V, are opposite. So it's still, though we're assuming that it's approaching the Earth, so what we're going to have here is going to be U minus V this time. C minus U minus V, F naught, right? Now, what we need to do, what's asked in part A is that we need to determine the speed of this motion, so the orbital velocity and velocity of center of mass of the stars. So what I'm going to try and do is I'm going to try and get U plus V term out of the first equation and U minus V term out of the second equation, so that I can add these two equations and finally find what U and V are. Now, in order to do that, first things first, we're going to have to take the square of this equation, right? So F plus square is going to be C plus U plus V over C minus U plus V, F naught squared. Now, let's multiply both sides by the denominator. So what we have then, let me put it here underneath. What we have is F plus squared times C minus U plus V equals C plus U plus V, F naught squared, right? And now then let's actually redistribute these. Same thing for the right-hand side. So C times F plus squared minus U plus V F plus squared is going to be equal to C F naught squared plus U plus V F naught squared. Now these two terms have the U plus V as a multiplier. Now let's group them, right? In order to do this, we're going to have to take this term to the left-hand side. So we're going to have C F plus squared minus C F naught squared equals U plus V for both. Then we have F naught squared plus f plus squared, right? Now let's go on the next page. Then we have c parentheses f plus squared minus f naught squared equals to u plus v f naught squared plus f plus squared. Now if we divide both sides by f naught squared plus f plus squared, these are going to cancel. F naught squared plus f plus squared. Now u plus v is going to be c f plus squared minus f naught squared over f naught squared plus f plus squared. This is our u plus v. Now, if we do the same algebra for the second equation, same path, please do it yourselves, then what we're going to find for u minus v this time is going to be pretty much the same. The only thing that changes is instead of f plus, we have f minus. F minus squared, f naught squared over f naught squared plus f minus squared. Then, again, in this equation, we're given everything, right? We know what f plus is. It is this value, 4.56891. And we're given f minus, and we know f naught. So we know all these terms, and we know the c. The c is also 3 times 10 to the power of 8 meters per second, right? So if we do the algebra and plug everything in there from here, our u plus v is going to turn out to be 5.25 times 10 to the power of 4 meters per second. And if you plug in all the values here in the second equation, then u minus v is going to be found out to be negative 2.63 times 10 to the power of 4 meters per second. Now, what we're going to do, we're going to add these two equations, equation 1 and equation 2, to each other. So when we do this, we're adding the left-hand sides. So u plus v plus u minus v is going to be equal to 5.25 times 10 to the power of 4 minus 2.63 times 10 to the power of 4. This is going to be equal to, let's look at the left-hand side. There is a u here and another u. We have two u's, but these are canceling out. So 2u is going to be equal to the 2.62 times 10 to the power of 4 meters per second. So if we divide both sides by 2, then we're getting u to be 1.31 times 10 to the power of 4 meters per second. Again, it came out to be positive, right? Positive. This means the star system, the binary system, it approaches the Earth, right? Now we know u. Either you use this first equation or the second equation to get to v immediately, right? We can do that. So we said that u plus v was 5.25 times 10 to the power of 4 meters per second, and we found out u was 1.31 times 10 to the power of 4 meters per second. Then v is going to be, as you can see, 5.25 times 10 to the power of 4 minus 1.31 times 10 to the power of 4. Then our v, the orbital velocity, is going to be 3.94 times 10 to the power of 4 meters per second. All right. Now, in part B, we are given the period of this movement. So it's 11 days, right? And we're asked to calculate the orbital radius. We're going to call it R, and the mass of each star. And lastly, we're going to compare the orbital radius to the distance from the system to the Earth, right? And there's a comparison part. Now, How do we get to the orbital radius if we know the period? Is pretty straightforward. 2 pi r would be the circumference of this movement. So for one star to come to its original position after one revolution, this is the distance that it has to travel, right? 2 pi r. That is going to be equal to the orbital velocity of it times the period of that movement. So if we divide both sides by 2 pi, then we know what the orbital radius is. This portion is pretty straightforward now that we know the orbital velocity already. So the orbital velocity was 3.94 times 10 to the power 4 meters per second. So please pay attention to the units at this point, because we're gonna have to convert 11 days into seconds. If you like, we could do it on a separate base here, or we could actually do it on here. Now that we have 11 days, right? And each day we have 24 hours a day, correct? And then we have 60 minutes per hour times we have 60 seconds per minute divided by 2 times 3.14. So we're basically multiplying. Got a little, I ran out of space here, but it's 3.94 times 10 to the power 4 times 11 times 24 times 60 times another 60, right, to get to seconds. So then if we do everything correctly, the orbital radius is going to be 5.96 times 10 to the power 9 meters. And now while we're at it, remember how we were asked to compare this to the distance between this system to Earth, and the distance of this binary system from Earth was given to us. Oh, sorry, we were asked to compare this distance to Earth-Sun distance, right? So the distance from the Earth, let's keep this in mind, distance from Earth to Sun is actually 1.5 times 10 to the power of 11 meters. So it's actually, when you're looking at the powers here, it's much greater. If you want to see the ratio, let's take the ratio of distance from Earth to Sun divided by the r that we have, the orbital radius we have, 596 times 10 to the power of 9 meters. You're going to see that it's almost 25 times. So the distance from Earth to the Sun is 25 times greater than the distance of, this orbital radius that we're talking about. Now, going back to the last part, we were asked to calculate the mass of each star. How are we going to do that? Again, let's remember that we have 2 stars, right? So the gravitational force between the two, it has to be equal to the centripetal force, right? So if we write the gravitational force between the two, gravitational constant, the first mass, the second mass, over distance between the two. So the distance between the two would be 1 r from one star to the center and another r. So then it's going to be a total of 2 r's, right? So if you remember the formula, in denominator we have r squared. So then our r happens to be 2 r's. Now, the centripetal force, if you remember, is m times v squared over r. Now, all we need to do is to solve this equation for the mass. So 1m is going to cancel 1 out. And then let me rewrite, let's isolate m on the left-hand side. Then is going to be v squared over r. This is going to go, and 2r squared is going to be 4r squared, right? Divided by g. Now we have 1r and r squared here. So overall mass is going to be orbital velocity squared. 4 times of that times r over the gravitational constant. So at this point we know everything. All the numerical values. Again, plug it in for v, which happens to be 3.94 times 10 to the power 4, square of this, and the orbital radius was 5.96 times 10 to the power 9 meters, divided by, our gravitational constant, 6.672 times 10 to the power negative 11. From here, the mass of a star is found to be 5.55 times 10 to the power 29 kilograms. Let's compare this mass to this is the star, right? To the mass of the sun, which we know to be 1.99 times 10 to the power 30 kilograms. As you can see, still the mass of the sun is one order of magnitude greater than the mass of the star. And if you want, you can take the ratio. So you can say m star over m sun equals 5.55 times 10 to the power 29 divided by 1.99 times 10 to the power 30. Then we find the ratio to be 0.279. So if you want, you can write the mass of a star in terms of the mass of the sun.